So overall, I'm going to be going over the photodegradation of optically active polymers, specifically the photocleavage of nitrobenzyl group, and being studied by the time-dependent excited state molecular dynamics. And I'd like to continue. Just overall, we're going to go over like the experimental introduction of what others have done, and then how that relates to the computational efforts that I have been conducting, and then just the computational theory and the analysis of computational outputs and the conclusion. So overall, in the past, members of NDSU, such as Dr. Seavey and Dr. Webster and Dr. Sivaguru, had conducted experiments where they combined a bio-based material to create a monomer, and they connected that monomer to a photo trigger, and they were able to polymerize the two, and they were able to actually decompose this or photocleave this molecule and recover this original bio-based monomer unit of FDCA. And they're able to do it not only with just the original molecule itself, but within a polymer format.
Can you give a definition of what is FDCA, just abbreviation?
Furan dicarboxylic acid.
Okay.
Furan dicarboxylic acid. And obviously you can see the unit there, which is in red. Okay. In general, what they did is they started with just a regular unit. It wasn't a polymer at this point. They just showed that the photocleavable nitrobenzyl group, if you shine UV light on it, will actually break off, and you should be able to recover the original molecule that you inputted. And then what they did later was incorporated this into polymers as well. And they were able to recover this unit in high fidelity, is their verbiage that they used. And so through our processes and how this connects to what we're doing with computation is there's kind of 2 or 3 main outcomes that we can get. One is we want to be able to see if we can get the same output as they have, which is the FDCA unit, as well as in their supporting information, as well as actually the manuscript itself, they did show a kind of like a browning, or what we would call a redshift, from the non-degraded to the degraded portion of their experiments. And so all that connects us, once again, is us to see the output of if we can retrieve this unit, as well as this redshift. The way we're going to be able to do that is actually ab initio molecular dynamics, and the subset of that, AIMD, estimates quantum mechanical Schrodinger equation, and it's estimated by the Hartree-Fock method. This allows trajectories to be generated using forces from electronic calculations, which is different than regular molecular dynamics, which uses Newtonian equations. And in general, we're going to be in this area of time and scale to molecular dynamics and quantum mechanics. So though that was like the general computational idea, what we're going to be using, I do want to be a bit more specific. This method was actually created by a few members of NDSU, such as Dr. Killen, I believe Dr. Hahn, and a few others, where we're actually going to be exciting an electron from one orbital, such as HOMO, highest occupied molecular orbital, into a different orbital that's usually beyond LUMO, lowest unoccupied molecular orbital. And during this excitation, it's going to be repeated where it goes from ground state to excited, from excited back to ground state, rinse and repeat, rinse and repeat. And how this differs from other methods is, as you can see on this figure over here, where we'll be having just in regular molecular dynamics, it would just all be in the ground state, and you apply the Newtonian forces that we talked about. For excited state molecular dynamics, this is just the electron being able to jump from one orbital to another, and you can see it here, but it does not transition back down into the ground state, where this TDESMD method is excited, from ground to excited, from excited to ground, and rinse and repeat over and over again. And in general, this cyclic population and depopulation in orbitals changes the orbital occupation, which will vary the forces between the atoms, and this will force the atoms to obviously diverge from each other and exhibit photofragmentation. And so in general, it's that cyclic population and depopulation, rinse and repeat over and over again, and the forces will change throughout this process into what you would see as in different fragments. So to start off with our particular, let's say, experiment that we've conducted, part of this process we have to look at what's called density of states, which is the occupation of the orbitals. And the red on the graph here would indicate the electrons occupying these orbitals. And you can see the figure themselves, which is my molecule as shown here, which is similar to what I had shown previously describing the experimentalists portion. And then this portion over here on the right is where no electron would be, okay? So I do want to say that during our excitation and de-excitation processes, we would actually be taking the electron from here and putting it over here. And I wanted to highlight that this would usually be empty, and then this portion would be red over here. And the reason that we're doing this is to actually see which orbitals would be possible candidates for this process to work. So, for example, if we move an electron from 109 to 114, that may not show any sort of fragmentation compared to an orbital from 112 to 116. And so we need to be able to see if there's even a possibility for this to occur. And this is how we tell. As well as this, where the transition energies of our system, I believe maybe the viewers can correct me on this, is the probability of, the higher the peak, the higher probability of a transition occurring, transition energy, as you can see. And in general, at each peak, you would see some sort of fragmentation throughout our different orbital combinations. So in the previous slide, I had explained how from 112 to 116, we have to physically place that and do a calculation with that. And we saw a large number of decompositions. The red X's are indicators of bonds breaking in this case. In other orbital combinations, let's just say orbital 110 to 116, only a couple bonds had broken. Over here as well, and so on and so forth. And so just looking at the one that had decomposed the most, which is actually the highest peak in this transition energy graph, was a good start to at least analyze our simulations. So in our simulations, just for, it's like a double check, is we're going to have being two conformations, okay? In this case, I'm going to start with what I called as a monomer, or excuse me, what Dr. Killen and I have declared as a monomer. And in this case, Dr. Killen had done some calculations with H2O with this monomer unit, where it's just the benzene ring by itself, or connected to a furan portion, and then it's in a periodic box where it wraps around and connects back to the benzene nitrobenzyl group here. And I want to notice some unique things about the orbitals, is how these p orbitals pretty much throughout the whole molecule exist. So you can see that in the benzene, portions of the carboxylic acid group, and the furan group. And then also, that being the same for not only HOMO -2, which is orbital 162, but orbital 167. I probably didn't do a good job of explaining how there's going to be different orbitals involved depending on your figure or the conformation that you're using. In this particular case, the HOMO was 164 and the LUMO was 165, I believe. And so the unique thing about this conformation, one of the double checking is you'll still see this type of, let's say, orbitals throughout our monomer unit, even on the HOMO and LUMO portions, HOMO -2 and LUMO +2. There is a slight difference, and I believe it's the pi-pi bonds in their, let's say, electron densities compared to the HOMO -2 portion. This difference with our second let's say, conformation, which is a dimer, which we have a total of 2 units. So let's just say 2 benzene ring or nitrobenzene rings and 2 furan groups will be connected in a long strand. And you'd see that there's a difference in the homo-lumo molecular orbitals. In this case, we have the pi, I believe it's pi carbon-carbon conjugated bonds in the furan group, expressing high electron density, whereas more in our LUMO +3 we see carbon-carbon bond between the furan group and the carboxylic acid, showing these slight differences, but it can help us analyze things in the future. We need to look more in detail on those. What I'm about to kind of express is during our simulations, we generally have like a unit that's connected as so. It's all connected. Hopefully visually we're looking at the closest end is the darker part and the further end is the lighter part in our visual screen. And throughout our excitation process, you can see how stuff disintegrates and moves, or cleaves, excuse me, and moves throughout the simulation. I just want to explain that to you, so hopefully you understand the next portions. This may be not the best time, but I think it's fair that I need to explain the mechanism of possible, let's say, cleavage. Generally, in papers that I've read so far, they say the primary reaction is usually due to an abstraction of this nitro group. It gets excited through the intervention of UV radiation, gets excited, is able to take or abstract a hydrogen from the neighboring carbon, and it creates, like I believe they called it a biradical unit, and it was able to go into different nitro portions such as Z and E, and this is kind of the primary mechanism of any sort of cleavage to occur regarding this and whatever it is attached to. And so I wanted to explain that ahead of time before we kind of looked at the possible mechanisms. Through our videos, I could have shown the videos, but due to time and just ease of viewing, I wanted to break it down in an easier format. And in general, what we saw with the case of moving one electron from one orbital to the other, in this case from 162 to 167, we saw fragmentation occur at this part right here. And it's actually able to generate this molecule and this molecule as well. And through the processes of interacting with water, being excited, an oxygen was actually abstracted, taken from the neighboring environment, and input, as you can see here, connecting to this carbon that was, let's say, disconnected from this oxygen portion. One of the oxygens from the nitro group actually went back into the environment and had been involved with interacting with the hydrogens that have been, let's say, decapitated from the original oxygen from the H2O group. How this can relate, I'm still trying to analyze or understand how this, let's say, relates specifically to the orbitals. I believe there is some connection that could be made. For example, there is some sort of electron density in the carboxyl area where this segmentation broke off, and it's just trying to see how and where that occurs or why that occurs. Excuse me, there isn't. Actually, where it's broken, there isn't any electron density, so I have to see why that is or how that can relate to this decomposition. So in the case of monomer, this is just a single unit. We were able to do this calculation in water. In the case of dimer, which is a bit larger, we've only been able to do it in vacuum so far. And throughout the long simulation process, it actually had broken off in many, many different places, and it decomposed in many different forms. It had nothing to interact with. It was just the energy inputted by, quote unquote, the excitation and de-excitation. As you can see, there's very numerous number of units decomposed. These red X's that I'm showing are actually meant to be just the first set of decompositions. So for example, as you can see here, red X shows the bond had broken between the oxygen and carbon and these two carbon bonds, and it generated CO2. NO2 had broken off. And over here, just due to the periodic box, this CO2 group had been able to connect back to the benzene ring, which was originally part of the nitrobenzyl group. Over time, all the other, let's say, changes that you see had occurred, but I just wanted to show the initial or primary mechanism. The thing is these don't seem to match that original mechanism I had brought up that I've seen in what other papers have suggested, such as for that O-nitrotoluene group. In this case, if you look at the orbitals, though they're surrounding the Fran groups in both scenarios, it seems like decomposition occurs elsewhere throughout the, let's say, the molecule or dimer unit. The thing that we did see, we were able to see through the absorption spectrum is actually a redshift, which I showed you previously in the earlier slides. The absorption spectrum was conducted, and this was before excitation, and this is after. Though this may not match specifically what they have found as in quantitatively, we wanted to see a qualitative redshift, which we believe we have seen regarding these different excitations before and after. That was just for the monomer 2 unit. This is with H2O, and compared to, let's say, the dimer unit, I am still trying to construct the absorption spectrum at the moment. I'm understanding that there needs to be intermediates that I need to look into, which have affected my original absorption spectrum, which I have not shown here for that particular reason, for the dimer unit. I do wanted to emphasize the monomer H2O mass spectrum. We were kind of looking for, because of the FDCA unit that the experimentalist had originally recovered, we wanted to see how that would relate to our mass spec simulation. And as you can see, though, it may not show a high peak, but in this particular case, this mass spec, which is the molecular weight on the bottom, and the let's say the amount of time it was present in the simulation, it doesn't seem to correlate that well. But it was seen visually. It's just not up for a long period of time. For the NO2 group, it may have been shown a bit longer. As you can see, it matches quite well with this little peak over here. These large peaks that you may see to your far left would be, I believe, the hydrogens, and then the H2O molecules inside of our simulation. And on the far right is our original molecule. And then all these are the fragments in between. Once again, we wanted to see if we could find this unit throughout our mass spectrum data. That was for our monomer unit. In this case, for our dimer unit, which was once again in vacuum, we try to see its location throughout the mass spec of all the different fragments. And some of them have been able to correlate well with differing peaks. I believe this large peak that we see here is actually just a combination of these, let's say, 4 groups, all relatively having the same molecular weight. And so in our conclusion so far, we have computational trajectories have been successfully conducted. Photocleavage of the molecule was seen in water and vacuum simulations. In between the water simulation versus the vacuum, our water simulation seems to show, let's say, better results relative to experimental. Photocleavage mechanism in water, matches literature. That is not true. I need to address that. Redshift is seen in the absorption spectrum in water, and further analysis of the photocleavage mechanism will be conducted. And I need to acknowledge Dr. Roslev, Dr. Killen, Dr. Han, and then my partners, Nasuke Queenie Iluoku, Department of Coatings and Polymeric Materials, Center for Sustainable Material Science, North Dakota State University, and ND EBSCOR Award, and 135546. Okay, thank you. And that is all.
Okay, please join me thanking Meade. And everyone is welcome to like unmute microphones.
I see there's a lot of questions, which I can address.
Yeah.
And that's good. That's good.
Yeah, let's check if anyone wants to offer questions right away and ask it verbally, and then we can go over the list.
May I have a question, Dr. Kulin?
Please, Amir.
Hi, Meade. Thank you for the presentation.
Yep.
Just a question, a technical question about the plot, the absorption spectra from the molecular dynamic model. Can you briefly let me know which code did you use or how did you plot this spectrum?
Actually, Dr. Killen did this portion of the absorption spectrum.
Meade, it is not a legitimate answer. I will not do the presentation, so you should try your best.
Which code?
How did you plot that? For instance, how did you extract the data from the outcar file? How did you, because for each time step, I think we have some orbital energy results. So you need to go through them, maybe getting some average or, I don't know, some post-processing calculations. I should do that for my project also. So I was just curious if you have any package or Linux code to do that.
Well, the issue I was having was actually quote unquote intermediates, cool intermediates, where it seems like throughout our process we have to, at some point in our simulation, you have to do something to be able to get this absorption spectrum. I actually have a visual of the absorption spectrum that I got, which is not as good. So this is the one that I'm trying to do, and what I was simply doing is taking the car file from the from my simulation. Let's just say on the very last frame, I was taking the car and just simply doing the simulation or the absorption spectrum process that we were taught in class, and this is what I was getting. Obviously, something's wrong here, and in particular, Dr. Hahn informed me about how the kinetic energy in our system is quite high, so I need to be doing some sort of intermediate step, or maybe I use this frame but cool down the quote-unquote fragments, which I need to talk to Dr. Killen about that. So,
just a second. The question of Amir was not so sophisticated, and he was not accusing you of doing something wrong. Please, I believe you do have backup slide number 58. If things were, if I have the same set of slides. No, it did change. But just general, oh yeah, here 60, now it is 60. You can just explain general principle, what your understanding of UVD's spectrum, and then that approximately it can be considered as electron being moved from occupied to unoccupied orbital, and for these pairs of orbitals one can set up the transition dipole and oscillator strength. Just give basics. You do not go into thermalized state after long excitation.
Let's say regarding that transition energy diagram which I showed, we would get that information from this OS strength file, and this would give us important information to determine which, let's say, orbitals to look at, and in that case we could focus on them and get some sort of electronic information. You know, I actually specifically don't know the details, and so this is a good moment to explain how these dots are connected, because I'm somehow supposed to be connecting transition energy and oscillator strength to absorption spectrum, which is quite difficult.
Okay, but difficult but doable, right?
Yes, yes.
And probably there will be not enough time to for the audience to torture you about details. You can promise, like, give me another like time slot for 1 hour, and I will teach you how to do it. But just show that you are aware of basics, what is going on. So that you're describing how electron is jumping from one orbital to another under laser field.
Yeah, and so the question is how does that relate to like absorption spectrum? I honestly have no connection with that. That is a very good point. Like I see here that obviously we have the electron from the initial orbital jumping to the final, but how does that relate to absorption spectrum? I have very little understanding on that. Like I don't know. It's a good question. Maybe I'll ask a student after if there's not enough time now to explain it.
So let's check if there are more tricky questions that would confuse me.
Yeah, let me just write that down.
So if there are, let's wait for more questions formulated verbally, and if no, I suggest we should go through the chat line and go one.
Okay, just a couple of comments what I have. Yeah, the Meade, that's a good draft. I'm still thinking from the CSNS presentation point of view. So that's a good draft, but probably we have to a little bit reformat it, since we are going to have quite wide audience over there in topics. So in your introduction, the first slide is supposed to be not just the paper, but overall topic you're working on. And then you're going to talk about the paper, which we used as the as a basis for our food research. Okay, so you probably need to talk about that you're interested in the degradation of the polymers, and then in this kind of part of research, what you're going to present, you're particularly going to focus on the photodegradation using computational methods. And then just go with this paper, explain what in this paper, and then, right, and another comment, please again, take a look at the names of all these compounds what in this paper involved, and try to memorize the names of them. So because you cannot say not this unit, you have to say each of these structure by name. At least these 2-3 main structures, okay?
Yeah.
Otherwise, it looks a little bit odd, when you're just saying, oh, not this unit.
Yeah, okay.
Okay. The same comment for another word, what you say, the decapitated. It's attached, some more chemically related words.
Yeah, I can do that. Yep.
Okay, and the rest, yes, like more what the Dr. Killian can comment on, and then later I'll probably talk to you directly, or we will, 3 of us, just get involved in some discussion, maybe through the email. So we'll see.
Okay.
Thank you. But in overall, quite a good talk. Yes, so we can just improve it a little bit, and it's going to be really good. And yes, and try to talk no more than 15 minutes. Otherwise, it's getting too large for CSMS kind of reporting tool.
Yeah, was that
This time it was 20 minutes probably.
20 minutes? Okay, yeah,
Yeah.
thank you for okay.
Okay, Dr. Killian,
If Meade recites it once again, like in so to say, in a bathroom or stay alone in the room, it will be quicker.
quicker. Okay,
Yep.
yeah, I
It
hope
just
so.
goes longer when one is trying to find words speaking for the first time, or if one goes over the same slides again, it gets like 70% quicker. There is a, before we go to systematic scrolling of all comments, there is a third from the bottom question from Yulun. Who is your audience? So probably you and Professor Rasulov know about it, but the rest of the attendees of this meeting do not know. Can you please tell us whom you are communicating this story?
So this is being specific. It's the Center for Sustainable Material Science, which this includes all members or many members of, let's say, the chemistry department, polymer chemistry department, and I believe even like Dr. Owen of the mechanical engineering department, that general range of physical chemists and polymer chemists and even engineers. So these are the people that I'm involved with. I don't think there's any computational personnel other than myself, I think.
Okay, so you will be the strongest computational chemist in the audience.
Yeah. Yep.
Okay. Very good, very good. This ambition. Okay, and if there are immediate questions to ask verbally, please go ahead, because the list of the typed questions is a little longer than usual. Okay, and I'm going to read and pronounce my questions, but anyone is welcome to step ahead and keep going. So, Meade, would you please go to slide 6? Okay, it's
This one?
next one, 7 in your. Okay.
Yeah.
So you are showing the equation. What is H? What is H capital?
But it's the oh my gosh, I don't want to say it's the wave function because it's not. Oh my gosh, I knew it. Why is it forgetting now? Hold on, let me quickly look. I don't want to say it's the Slater determinant because it's not. I apologize.
Okay, that's the first question what Dr. Sebi gonna ask over there, you know?
Yeah, okay.
What is H over there? He understands all these things, so if he, even if he is not the computational person.
Okay. Oh, H is the operator and E is the energy of the system. H is the, yeah, well, it says it's the operator, but specifically what type of operator is the question.
Okay. And so it's total energy of your molecule, right?
Say that again?
It is, you are telling that it is total energy of your molecule, of your polymer.
I'd say of the system, the whole system. I mean,
so your whole
that's my guess.
Your whole system is polymer, right?
Yeah.
And your whole system is under irradiation by laser field. So how does laser field enters into total energy operator?
We're incorporating wave function energy into the system.
No, wait. If you do not know from scratch, just write down the question. It's the answer sounds quick and easy, but If you don't, just write it down. So the idea, and you'll go over technical details later, the idea is that laser increases energy of the system. So total energy under laser field somehow increases. And one day you may need an equation or verbal formula to explain how energy of system increases under laser field. Make sense?
Okay.
The Hartree-Fock method, I'm not sure it is applicable here. To my understanding, you were using density functional theory, which is different. So,
well, I believe, I mean, I was reading one of the previous documents, and it was kind of explaining the TD-SMD method, which used ab initio, which I believe is, let's say, estimated, or excuse me, the ab initio has to estimate the Schrodinger equation because it can't be solved. And I believe one of the methods is like Hartree-Fock, right? So is that not commonly used? So DFT is one.
You are reporting what you are doing. Or are your calculations done by Hartree-Fock? Are you 100% sure?
No, I'm saying. No.
Then it's safer to remove it. Just remove the whole line.
Okay.
Okay.
Yep.
Okay. And anyone is welcome to stop and ask more questions. Okay, let's go to next slide. So how do you introduce your circles, your Bohr orbitals? Why are you using them? I'm not telling you it is wrong or bad. It is a great idea. What is your idea? How do you introduce and why you are using them? Can you briefly state?
Why am I using different orbitals, or specifically in this diagram, why am I using circles as one?
Yes, why are you using circles?
It's just a simplified representation of, let's just say, an electron moving from one portion of, let's say, of a volume to another. This is just a kind of a simplified freehand version.
Okay, but please think on the background that you are describing molecules, and the circular orbitals in your diagram refer to single atom. So even if I do not have friendship with math and quantum theory, it is a little ambiguity. You are speaking about fragmentation of polymers and molecules, and you are showing orbitals for atoms. It is okay to use it, but then you need to make a disclaimer that I'm using this circular diagram to teach you guys what are the orbitals, because maybe you in the audience do not know what it is. It is your message. Or because I just find it's quite simple, but think about ambiguities and possible questions. Like, okay. Slide, 2 slides later. Okay, so what is density of states? What is the definition? Do you expect synthetic organic chemists to know what it is?
It's a well of energy. Yeah, it's hard to know what the others think because I haven't had that formal education that others have in this field. My understanding is it's like energies, and then you're gonna have, depending on where the electron is, it's gonna have a different energy in this quote unquote well, and so it's like different positionings of the energy inside of the wells. And that's honestly my understanding of density of states. And so,
Meade, you haven't said anything wrong, but you may just find online a verbal definition and copy paste it, either on the slide or in the comments, so that you can read it if someone asks. It's just a general style of presentations. Anything what is shown needs to be defined.
Yeah, yep.
That's right. That's a good comment. Everything yeah.
And second part of this question, like where this density of state is coming from. Are you drawing it by hand? Are you computing it by some method? There are so many computational methods. Is it density of states for the polymer that you are describing, or it is just schematic diagram of any density of states in the world? Just add specifics. So density of states or model for polymer blah blah blah. Add specifics and yeah.
Yeah. Yep. I get it. Yeah. Okay, I can do that.
Okay, let's go to the next slide. So you are given title of transition energies.
Yep.
Transition energies is only x-axis, but on the what is on the y-axis and which observable from experiment you are computing here?
Yeah, how it's relating to experimental, I don't know. I was looking as like
you do know. I didn't have an intention to confuse you.
Oscillator strength.
Oscillator strength is intermediate thing, and observable that comes from spectrophotometer is UVV's absorption spectrum, right? And this is the language that synthetic chemical audience and people who fabricate materials would appreciate. So you're showing absorption spectrum, right?
No.
No?
This is a transition. Later in the slides I'm showing absorption spectrum, but as of this slide in particular, I don't believe so. No.
Come on.
Really?
It is. I'm 200% sure that you are showing absorption spectrum. You are showing the response of the system to optical light at different frequencies. And then you are showing diagrams that excitation at certain frequency may lead into photoreaction. But the title is a little misleading.
Okay. Yep. Fair enough. It misled me. I had this on a previous set of slides, and so I guess I was trying to correlate that transition energy to how well it could degrade, and I was trying to visualize the orbitals and such. So.
Great. It is very correct logic. The talk is very well organized, and you have an excellent skeleton. Logic is, but there are multiple little things that can be easily fixed. So now there is a question of Yulun, and I believe it is a question exactly to this slide. What is the connection between decomposition and absorption?
Well, two things come to my head. If it absorbs more energy, it would, let's say, if the molecule can absorb energy throughout the simulation, it would have, like, let's say, more reactive atoms or molecules, and more stretching would occur, and so decomposition would occur. That's one. But then when you're asking for, let's say, absorption spectrum in the decomposition, such as why fragments have specific absorption spectrums, I could not tell you that, or specifically why.
No. Well, first let's ask Yulun if you did answer his question, and then I'll add a comment.
I guess, for example, in this figure, you have absorption spectrum. You also show the results of your decomposition. I guess that's your question is, what's the relationship between these two?
Yep. Okay. Okay. Fair enough.
So, Meade, when you started to answer this question, you did offered generally correct philosophical statement that the higher the higher the excitation energy, the larger the energy is communicated to system, the higher the chance that it will decompose. And for general audience, it kind of makes sense. But here you are digging deeper, and sometimes there are trends that if one excites at high enough energy, nothing happens. So the mechanism of decomposition is not as simple. You cannot say that the higher excitation energy, the quicker is decomposition or the larger number of fragments.
Yeah, I believe I've heard of the word using probability, right? Like higher probability this would occur. But or is that still wrong to use?
So if you have time before your presentation, maybe you need to work through the definition of absorption spectrum. And you have all components in your talk and in your head. You just need to make additional connections.
Yeah, yep, I agree.
So just definition of absorption spectrum would help you to interpret this slide and present it better.
Yep, yep, okay, okay.
There is a comment from myself. It's not a question, but in some sense, I'm answering to you that the spectrum that is demonstrated on this slide is absorption spectrum which corresponds to very low intensity excitation for absorption of only one photon. While decomposition happens if one peaks transition energy course where we have peak and absorption and communicate more and more photons at this energy. So it is not a literal connection. If you have just absorption spectrum and submit one photon, reactions highly likely will not happen. We select at which transition energy the polymer is able to accept energy, and then we send more and more photons there until it decomposes. So absorption and decomposition are not equivalent.
Okay, okay.
So
yeah, so yeah, like you said, this you believe this diagram is misleading? Is that kind of the?
It is not misleading. The diagram
is not.
The diagram is excellent.
Okay.
It is just not presented with sufficient details.
Yeah. Okay. With sufficient details. Okay.
Please keep it. It is maybe it is the if you offered to keep only one slide in the whole presentation, this is the most important slide. It summarizes everything. So if you are about to remove something, anything but this one.
Thank you.
Okay, and in the chat comments, the numbers are a little bit off because maybe you made last-minute changes. So numbers in the chat line and in your actual presentations are off by 1 or 2. So let's look on next slide.
Okay.
So
okay.
On the left and the right, your models look disconnected. And if I'm just random visitor to your talk, I do have a big confuse because you are telling that here is the decomposition of an intact long polymer, and right now you are showing orbitals of an object that is already teared apart. So a polymer before reaction should be like a continuous thing. How come that it has like void in the middle?
Yeah, are you talking about the slide I'm on right now?
Yes.
Oh, okay. You believe that there's voids? Oh, so just here. Okay. Yeah. Okay, I can clarify that these are two different views of the same like molecule and its orbitals, just to show just another perspective of the same scene.
Okay, then you need to verbally describe it, or maybe put a second view in the box and present it as an insert, you know, like put in the box and then make lines, just explain what it is. Because
you need to clarify it, right?
It is a little confusing. It looks like it is orbitals on the molecule that has been already broken.
Yeah, I see what you're saying. Okay.
And there is no reason to criticize you because you did everything excellent. It just little think on the way it is presented.
Yep, makes sense. Okay.
So what is, for this and next slide, also a little technical question that maybe there will be no time to discuss it, but be ready to answer. What is periodic boundary condition? And why do you need to implement it while describing polymers? Like maybe you need to show more than one of replicas to show that it is an infinite polymer, and you just focusing your view on one unit cell.
Okay. Okay, I can put in that effort to do so. Okay. Fair enough. Okay.
Let's go 2 slides forward and one more. Yeah, this one. I feel the hand of an expert in organic chemistry here. And by the laughter, I make a guess who is this expert. So in this diagram, in the first reaction step from reactant to the first intermediate, you have brackets and you have a label on the upper left with number 1. In the next step, you have upper left label 3. What are these? Yes, 1 and 3 numbers.
1 and 3. That's a good question. I didn't even notice it when I was reading that paper.
Who is going to answer the Meade?
Well, Meade is the author, main author of this work, so everything what is shown should be explained.
You know, specifically looking at this paper, and I guess it doesn't even recognize it. But,
you'll have to read it now to find out what is that.
So,
yeah. Okay.
That's a multiplicity.
Yeah, it looks like singlets and triplets. So this changes spin multiplicity. And now the question is: does your calculation includes spin flips change of the multiplicity? And if yes, then you should brag about it. If no, then you shouldn't provoke the question, because audience may read it and tell it like, if the main part of the reaction is a flip between singlet and triplet, and you do not have it, then everything you show is wrong.
Okay.
Just think. Or there is a little way detour. After you have your first intermediate, which is singlet, you have an arrow down, which goes through reaction of the. Can you navigate with your mouse? Yes, yeah, this one. So this one is formed without spin flip, and this reaction path can be done without change of multiplicity. So this one is likely available to describe. While for the other wing of the reaction, one needs to redo calculations with spin flips, which is possible, but it is a different calculation. So just be aware of this.
So what you suggest to redraw that kind of figure without the compounds which are in multiplicity more?
No. We shouldn't decept the audience or hide facts. We can either remove the complete diagram, or we can tell like we are able to describe first three intermediates, first, second, and the one on the bottom. For other ones, yes, we need to redo calculations with triplets. Mm-hmm. Therefore, we need another year and another million of funding.
Right.
But there is a possible, like, if the audience will be in the mood to find errors, it is one of the big places where they can pick.
Right, I think. They can start asking too many questions in this case, so it's better to avoid it, especially for this kind of meeting.
Okay.
Okay.
Let's go forward. No, not also. You're removing this slide, okay.
Yeah. So we were.
Just keep things okay. Just this one is okay. So this one is great, and it is probably what audience would be really happy to find: cleavage of one bond and insertion of the dissociated order. Let's go to the next one. So there are a lot of small fragments. When you were reading the paper by Sivaguru Jayaraman, do they mention this fabrication of many small fragments? How realistic it is?
Well, they didn't really discuss the all they cared about is that FDCA unit.
Right.
So everything else.
Exactly. So in this diagram, it looks like the reaction that you were modeling went too far, which would correspond either with us on a real experiment, focusing very high intensity laser that is about to burn the polymer, or we expose it to regular light, but for a very long time. So it decomposes on too many fragments. Instead, on real experiment, if it is not our goal to burn the polymer, we can just irradiate it for shorter time or with lower intensity. And in the simulation, it would correspond to taking the shorter part of the trajectory. So indeed, for this pair of orbitals that you are indicating with blue and red, the reaction seems very vivid. And it decomposes to a lot of fragments in a short time. But I afraid, or I foresee that organic chemistry audience may put a doubt that decomposition of a polymer, the cleavage of so many bonds is realistic. So you may keep everything as it is, but just plan to make a comment that this is a diagram of what would happen if we overcook it, if we do irradiation for a long time with very intense light. Make sense?
Okay.
And everyone is welcome to contribute to discussion or overcooking. Okay. Maybe even put the.
That's right. So what is better, to remove these small fragments, right? Or he needs to explain it in addition what's going on?
It's better, but explain.
But explain. Okay, Meade, so yes. Please. Yeah.
Meade is presenting for this audience for the first time, I think. It is
no, that's not the first time. But this kind of research, the first time, before we were presenting some other stuff.
If it is not published, if it's work in progress, then it's like in operating the cannon. If you put too much gunpowder, the projectile will go too far.
Yeah. Yeah, the Meade, you also need to keep saying that this work is still in progress, and still we are getting the results and you know, the tuning the method.
Okay. Okay.
Okay. Next, yeah, this one. So you explained it very well by telling that computed spectrum is not ideal and it is too much redshifted. And do you have an idea which practical steps in computation you can do to make the spectrum more realistic?
More realistic?
Yes, to avoid its exceedingly strong redshift.
I know there's other options, but I don't know specifically the terms used. Would it be like, you know, different spins or anything like that? I don't know.
Amir may prompt us what to do.
I'm not sure. Are you thinking about the key point sampling to get?
No, this polymer is not conducting. What else were you doing to make your spectrum more realistic? Which function did you use?
Oh, yeah. You mean about the accuracy of the job? So we did HSE06 hybrid functional groups.
Yes, yes. Just by repeat single. Thank you, Amir. That's a great idea. So by using hybrid functional available in the last HSE, just single point, it will remove this exceedingly redshift and make spectrum more realistic. So even if it is not done, you can, if anyone will have objections or questions, you can tell that I do have a way out to make it better.
Okay. I'll talk to Amir if I need it. Okay.
So then slides 15 and 16, question from Professor Rasulev. Why main structure are in mirrored representation? I think it is a few slides backwards.
Yeah, because he added a couple of slides now.
It is with orbitals.
Yeah, you probably mirrored this structure, the main structure, because NO2 looks like, you know, 2ON. It's not supposed to be like that. Why you did that?
Okay. Yeah, I can.
Just, you don't have to do that right now. I mean, put in back.
Once again, if it is just graphical image, you can just flip it.
Yeah.
Right, that's what he did at the very beginning, probably. You know, he just flipped it.
Yeah, I can.
Maybe unintentionally. Yeah, I understand.
Okay.
Yeah. You know, for us it's okay, but there are some synthetic chemists see they may be a little bit.
Okay. Actually, this is actually with the program.
Really?
This happened here too, where I didn't flip it. Yeah, it's with Chemdra. I think it might automatically do that sometimes. So I can see if I can change it, but it might be just the software, to be honest. Is it just NO2? I guess the RO over here. I'll check on it. Okay.
Okay. So next.
Yeah, and yes, and in this case it's kind of strange. N2, that's what's going on. So that's definitely not right.
Yeah, I'll look into it. Okay.
About this slide, I think I left another comment, but we already discussed it. So if one So it's more technical question of discussion for Professor Rasulov and Dr. Khan and me as well. But if we do not want to spend too much resources and time, so we can take trajectory that has been already computed and then truncate it in the middle or in the like 70%, and then use truncated trajectory to regenerate the mass spectrum. I think this question is two slides later. Can you please, yes. So here, the fragments that are expected from the literature are very small fraction. The peaks corresponding to this fragment that you are indicating are in minority, while there are so many other fragments which likely correspond to overcooking of the system and going to a lot of smaller molecules and radicals. So if we want to improve, to avoid this overshooting, this overcooking, one can probably take the trajectory that you already have, truncate it, and then process it the same way as you already did to compute the mass spectrum. There are expectations that it will increase relative proportion of the healthy products that Meade is indicating with arrows. This furan dicarboxylate and nitrobenzene group. So it's just a comment for discussion in future calculations.
Yeah, yeah, okay. Yeah, I just to clarify, it was like, rather than going to the extent of, I think this goes like for like 2,300 quote unquote shots, it would actually go down to, we could do like 1,800 or something. We would choose that number.
Yes.
Yeah.
Yes.
Yeah.
And
Okay.
again, your personal resources and personal time is limited. Our astronomical time is limited, but hypothetically, one can consider truncated at 1,700, 1,800, 1,900 with the steps, and do mass spectra for each of them.
Oh, okay. Yep.
Show how the reaction goes as we expose the polymer to light for longer and longer time.
Yeah. Yep. Okay. Yeah.
Like if one makes it too short, then there will be only single peak corresponding to the whole polymer, the rightmost peak on your diagram. And as time goes by, it will develop this main fragments which are about 2 times lighter than original, and then there will be popping up smaller molecules close to zero. Like
yeah. Yep. Okay. Yeah, we can discuss that.
So, if you need to speak about your talk without your slides, can you formulate it in the following language? Like, what was the most scientific hypothesis, intuitive hypothesis, that you tried to prove with numerical experiment?
Well, the two things, which is such as the mechanism, but we'll start with actually the redshift is we were able to confirm that redshift did occur computationally, which matched experimental results. Now, when it comes to such as the mechanism, we're still under analysis to see how well that relates to experimental, let's say, literature, and see how well we can compare that with them. That is still under analysis or work at the moment.
Not bad, not bad. Yep. You can maybe even put it in conclusions or in the introduction of both. And if you will be developing and presenting this talk to other audiences, you may develop this statement, but as described is good. It makes sense, and it may be a little simplified, but it is a good like compass to.
Yeah. Okay. Fair enough. That's a good thought.
There is one more comment at the edit while we were speaking from Yulun. Maybe you can brag and give details about. You were laughing like maybe you can brag. Period. Maybe you can give some details about the mass spectra. The computation of mass spectra is not a standard, usual approach in the community.
Yeah, I'm happy to. The thing is, it's more like I could see a lot of questions come up if I keep, I guess, making a large portion of the product of not necessarily how did it occur, but I know there's a whole, let's just say, paper on reviewing this performance with other methods, right? Which actually I have a portion of, and right here. And like, if they ask how does these compare that well, I guess we'd have to see. Yeah, I can. That's an option. Yes, yes, that's an option.
And since the time is limited, you can always give a disclaimer. Like in this talk, I'm answering what is happening rather how it is computed. If you really want, please invite me once again, and I'll give you details. Maybe they will not follow this suggestion, but it will kind of navigate the attention to applied results rather than methods.
Yeah, I agree with Dr. Killian. If you start getting some kind of, too many questions, you can always say that I can give you details later. I mean, we can talk outside of that CSMS meeting, and I can answer all your questions. So not to get into, the really detailed discussion during the meeting, okay?
Okay, that's, you actually want me to put that on the slides or just discuss it when I'm over after the acknowledgements? Oh, by the way, like if you have, like, or you're saying as they're questioning if it goes too far?
Well, I believe we are in perfect timing. We finished the discussion at 6, literally.
Yeah.
And there are no more typed questions, but I think the connection is not will not be broken automatically right now. So if there are more questions or suggestions to Meade, please feel free to verbalize. Or
Dr. Killian?
Yes.
May I have a question from you or Meade? Also, feel free to answer. So you mentioned about improving the spectrum, absorption spectrum results by using a hybrid functional. So if the model is not conductive, hybrid functional are still are a good choice to improve the results, because I heard that these hybrid functionals usually are recommended for the conductive or semiconductive materials.
Yes, this is correct, but it will be not ideal, but better than plain than regular DFT GGA-PBE that was used. So the original functional used in this calculation was Purdue-Book-Ertenkopf, which does not have the Hardy-Fock exchange. This is very quick. So it is much quicker than most of other functionals, and therefore it is used for molecular dynamics and photo-induced molecular dynamics. But this functional is known to give overestimation of the redshift. So it typically shows band gaps smaller than they are. And basically, most of modern functionals would fix this stuff. And the HSE06 is maybe the first choice to try.
Okay, thank you.
I'm sorry, what was the exact name for this? What was it called? I didn't.
HSE 06. This abbreviations stand for last names of 3 scientists who designed this functional. Hyde, Skuzere, Erzenhoff, and it just uses contribution for Hartree-Fock exchange added to the total energy, so which increases the gap.
Okay. Okay, good. Thank you. One last thing. I just want to clarify with the acknowledgements. How did you guys want me to write this? Just nurse? Is it? Are these supposed to be connected? So like nurse.
No, these two different ones.
No.
Those are different.
Okay.
That's NSF. The last one is NSF CHE.
Yes. So
NSF.
National Science Foundation.
Leave a space in between them. Space. Yeah.
I'll read into this real quick before, just to check on the title. Okay.
Yeah, for nurse, I think you can use the logo. You find it online. It will be same as you have this CSMS and Export. There is a single logo online, and there is like there is nothing to shame about it. It's more like brag, because it's one of the like top, I don't remember, top 10 or top 50 supercomputers in the world.
Yeah. Okay. Maybe I can just do that.
Oh yes. Thanks. Yeah. Super. Yeah.
Oh, it looks
Awesome.
nice. These nurse.
And this NSF CHE is like recent grant about the methodology on this photo-induced reactions.
Yeah, I'll look into it just to make sure I see it properly. Okay. Okay. Yeah, I will do my best and try to avoid stuff as much as possible, but also try to give enough information. Maybe. Okay. All right. Thank you, Dr. Killen.
Thank you, Meade. So,
Meade, also, sorry, Dr. Killen, I copy and paste the reference of the HSE functional in the chat box.
Thank you so much.
If it is the case. Yeah.
So,
okay, HSE paper. Oh, thank you. Yep, let me
Look.
mark that down. Okay, I'll just put it here for now.
So, Dr. Killen, what we decided, are we going to expect some updated version of the slides from Meade and then give some final comments or no?
I will not have time to provide more feedback. So please, maybe if Meade shares the slides with you and you just go over them, would be great.
Going to be good enough. Okay.
And I do not see if any slides can be omitted. It's quite condensed, and one can present the slides in 10 minutes if needed.
Okay.
Yeah.
Yeah, thank you, thank you. Yeah, but yeah, thank you for really good comments and suggestions. Yeah, it was really useful. I think Meade will be able to improve it significantly based on that.
Yes.
Thank you, Ilon and Amir, and for your comments and suggestions.
Welcome. My pleasure.
Okay, well, let me thank
you. Thank you
for inspiring discussion. We are meeting next time in a week.